In this video, we will learn how to predict the products of the electrolysis of aqueous salt solutions using the reactivity series. This video is about the electrolysis of salt solutions. But what does that term mean? The electro refers to electricity, and lysis means separation. And what are we separating? Well, a salt is another word for an ionic compound. So we are separating the positive ions and the negative ions in the compound. And a salt solution means that those ions are dissolved in water. A solution where an ionic compound is dissolved in water is sometimes called an aqueous solution. It is different from the liquid version of the ionic compound, which contains no water molecules and only liquid molten salt. So the electrolysis of salt solutions is the electrical separation of ions dissolved in water. Let's take a closer look. We start with a salt solution. For example, potassium bromide dissolved in water. The potassium ions and bromide ions float freely in the water. For visual simplicity, let's erase the water molecules, keeping in mind that these ions are indeed dissolved in water. The positively charged ion is called the cation. The negatively charged ion is called the anion. These two types of ions will be separated using electricity. The electricity in electrolysis typically comes from a battery. The battery is connected by wires to two electrodes dipped in the solution. Electrodes are typically made of an inert, stable substance, such as platinum or carbon. The unreactive electrode can pass electrons from the solution into the wire without itself taking part in the reaction. When the circuit is turned on, the charge of each side of the battery is extended to the electrode connected to it. Then, the ions are attracted to the electrode of opposite charge. In fact, the names of the electrodes and the names of the ions correspond to one another. The positive cations are attracted to the negative cathode, and the negative anions are attracted to the positive anode. Because a salt solution is made up of positive and negative ions, this process will occur much the same way regardless of the ions present. For example, here we're looking at a potassium bromide solution. But we could separate the copper and chloride ions from a copper 2 chloride solution in much the same way. However, electrolysis is not just about physically separating the two types of ions. There are also reactions that take place at the surface of each electrode that produce new substances. And in order to understand these reactions, we need to understand how electrons are flowing through the circuit. The negatively charged anions, with their extra electrons, are drawn to the anode. At the anode, the anions will donate their extra electrons. The anode will take those electrons and pass them along the circuit through the wire. Electricity is the flow of charged particles, and during electrolysis, electrons flow from the anode to the cathode. Before we look at what happens to the electrons at the cathode, let's look at what else happens at the anode. When the anions give up their electrons, they cease being ions and can form a new substance. In this case, any two chloride ions that give up their electrons can form a bond, making chlorine gas. The half reaction for this process is 2 chloride ions produce chlorine gas and 2 electrons. The chlorine gas will be visible as bubbles that form on the surface of the electrode. So, when chloride ions give up their electrons to form chlorine gas, those electrons are passed through the wire to the cathode. What happens at that other electrode? In this example, the copper cations have gathered at the cathode. The flowing electrons in the electrode are then donated to the cation in the solution. The two electrons cancel out the 2+ charge of the copper ion, resulting in a neutral copper atom that plates as solid copper. The half reaction for this process is a Cu2+ ion plus 2 electrons forms copper. In reactions like this, where a metal ion accepts electrons to form solid metal, we can see the metal form on the surface of the electrode. In this example, a thin brown coating will appear on the dipped portion of the electrode, but the color of the coating will change depending on the identity of the metal. Overall, this is the electrolysis of a salt solution. We've separated the positive and negative ions, and by passing electrons through the circuit, formed new substances at each electrode. While learning about the electrolysis of copper 2 chloride, we may have noticed that the chemical equations we wrote down look a little different than the chemical equations we're used to. Chemical equations, like the ones listed here, are known as half reactions. A half reaction shows the formation of one product as well as the electrons involved in that formation. Half reactions come in two different types. There are half reactions where an atom or ion gains electrons, and there are half reactions where an atom or ion, or in this case a pair of ions, loses electrons. We also have names for these types of half reaction. A half reaction where an atom or ion gains electrons is called a reduction. In this case, the copper ion is being reduced when it gains 2 electrons to form solid copper. When an atom or ion loses electrons, that's known as an oxidation. In this case, the chloride ions are being oxidized when they give up electrons to form chlorine gas. In fact, these two names can be combined when we talk about a full oxidation-reduction reaction. We could write the full oxidation-reduction reaction, where copper 2 chloride breaks down to form solid copper and chlorine gas. However, the half reactions give us some useful information about what is happening to the electrons during this process. Regarding the terms oxidation and reduction, we can remember which is which with a couple of handy acronyms. The first, oil-rig. Oxidation involves loss, reduction involves gain. Or, Leo the lion says grr. Lose electrons oxidation, gain electrons reduction. If oxidation and reduction take place during electrolysis, the reduction will occur at the cathode. Meanwhile, the oxidation will occur at the anode. The negatively charged anions are drawn to the anode, where they give up their extra electrons. Conversely, the positively charged cations are drawn to the cathode, where they accept electrons. For this particular electrolysis, the electrolysis of copper 2 chloride, the products are solid copper and chlorine gas. However, a variety of products can emerge when we electrolyze different substances. Let's take a look at what other half reactions are possible at each electrode in order to predict the products of electrolysis. One goal of this video is to be able to predict the products of the electrolysis of a given salt solution. In our example, the electrolysis of copper 2 chloride produced solid copper at the cathode and chlorine gas at the anode. Based on this initial result, it's tempting to say that the product at the cathode and ion will simply be the elemental form of the cation and anion, respectively. However, this is not always the case. If we electrolyze sodium chloride, also known as brine, chlorine gas will be produced at the anode, as we might expect because of the presence of chloride ions in the initial salt solution. However, at the cathode, hydrogen gas is produced instead of the solid sodium that we might anticipate. The electrolysis of magnesium sulfate produces interesting results as well. Hydrogen gas is once again produced at the cathode, while oxygen gas is produced at the anode. We've already learned about how some products are formed when the ions from the salt solution gain or lose electrons to form their elemental form. But what explains the emergence of these unexpected products that are not a part of the original salt? Let's take a closer look at the electrolysis of magnesium sulfate in order to find an answer. When the circuit is turned on, the magnesium ions will be drawn to the cathode, and the sulfate ions will be drawn to the anode. However, it's worth noting that these are not the only ions in solution. The strong electrostatic forces can pull apart the water molecules present in the solution. When pulled apart, each water molecule will form one hydrogen ion and one hydroxide ion. When those ions are formed, the negative hydroxide ion will be pulled toward the anode, while the positive hydrogen ion will be pulled toward the cathode. At the anode, instead of taking electrons from the ion in the salt, like when we take electrons from chloride ions to form chlorine gas, electrons are instead taken from the hydroxide ion, the ion that occurs when water is broken down. A similar thing happens at the other electrode. Instead of donating electrons to the magnesium ion from the salt, the electrons are instead donated to the hydrogen ion from the water. At each electrode, specific half reactions will form the products we see here. 4 hydroxide ions will give up their electrons, producing those 4 electrons, a molecule of oxygen gas, and 2 molecules of water. At the cathode, 2 hydrogen ions will combine with 2 electrons to form hydrogen gas. We now have an answer to the question of how these mystery products are formed. Depending on which ions gain or lose electrons in the solution, our products can be the elemental forms of the ions in the salt, or hydrogen gas or oxygen gas. But the question remains, how do we know which ion will be involved in the transfer of electrons? One key term to know in this video is discharge. An ion is discharged when it is removed from solution by forming an atom. In our examples thus far, when the ions are discharged, they form solid metals or gases. When predicting the products of electrolysis, a key question to ask is, what ion will be discharged? We have already established that at each electrode, there are 2 candidates that could be the discharged ion. It can either be the ion from the salt or the ion from water. The positive ions of each type will gather at the cathode, while the negative ions of each type will gather at the anode. Thankfully, there are a couple simple rules we can follow to identify which ion will be discharged. To understand the rule that applies at the cathode, we need to take a look at the reactivity series. The reactivity series is a list of metals in order, from the most reactive at the top to the least reactive at the bottom. With the reactivity series in hand, we can look at the rule for ion discharge at the cathode. If the ion from the salt is a metal that's less reactive than hydrogen, that metal ion will be discharged. Otherwise, the hydrogen ion from the water will be discharged. The metals less reactive than hydrogen are the metals below hydrogen on the reactivity series. These metals include copper, mercury, silver, gold, and platinum. These are the metals that will discharge to plate as a solid on the electrodes during electrolysis. These ions form atoms instead of the hydrogen ion because they require less energy to do so. Conversely, the ions of the metals above hydrogen on the reactivity series, like the magnesium from our example, require more energy to turn into an atom than a hydrogen ion does. So the hydrogen ions will be discharged in their place. We can use the identity of the discharged ion to predict the products of the reaction. Discharging a metal ion less reactive than hydrogen will produce the solid form of that metal. Discharging a hydrogen ion will produce hydrogen gas. We can follow a similar rule at the anode. The rule states that if the anion from the salt is a halide, that will be the discharged ion. Otherwise, the hydroxide ion from water will be discharged instead. The why behind this rule is similar to the why behind our other rule. It simply requires less energy to turn a halide into an atom than to turn other anions into an atom. The identity of the discharged ion determines the product of the electrolysis. If we discharge a halide ion, then a halogen gas, such as chlorine gas or fluorine gas, will be produced. In the absence of a halide, the hydroxide ion is discharged, and oxygen gas is produced on the surface of the anode. By following the rules we've described here, we can both identify the ion that will be discharged at each electrode, as well as predict the product that will be formed when that ion gains or loses electrons. There are several ways in which we can use electrolysis to our benefit in real-world situations. One such application is the restoration of artifacts. Over time, and especially when exposed to water, metal artifacts like coins, nails, and figures can develop chloride impurities. These chloride impurities make the artifacts look lumpy, dirty, and almost unidentifiable. Thankfully, we can return the artifact to its initial appearance by using an electrolysis setup with the artifact as the cathode. When the circuit is turned on, the chloride ions from the chloride impurities enter solution, where they are attracted to the anode. The chloride ions give up their electrons, pair up, and form chlorine gas, which bubbles at the surface of the anode. Over time, the chloride impurities dissolve into the solution, leaving behind a restored artifact with its original appearance intact. Another application of electrolysis is called electroplating. In this process, we coat a metal object with a thin layer of another metal. For aesthetic purposes, we may want to coat a piece of jewelry in gold or copper, or coat an exterior car piece in chrome. We could also coat a machine part with a certain metal to give its exterior certain properties, such as wear resistance or water resistance. To electroplate a metal object, we set up an electrolysis with that object as the cathode. We pick a solution where the metal ion in the solution is the metal that we want to plate on the surface of the object. In this example, when the circuit is turned on, the copper ions flow to the cathode. At the cathode, they accept electrons and plate as solid copper, resulting in an object with a thin outer coating of metal. In both of these situations, artifact restoration and electroplating, we can use electrolysis to manipulate the ions and substances involved to our advantage. Now that we've learned about the electrolysis of salt solutions, let's review the key points of the video. Electrolysis is the electrical separation of ions. During electrolysis, there's a battery connected to two electrodes. The negative cathode attracts the positive cations from the salt solution. Meanwhile, the positive anode attracts the negative anions. After ions are drawn to each electrode, they are discharged, or removed from the solution. When an ion is discharged during electrolysis, it will form a metal or a gas as a product. At each electrode, the discharged ion could be the cation or anion from the salt in the solution, or it could come from water, the positive hydrogen ion or the negative hydroxide ion. Half reactions show when an ion or atom gains or loses electrons, also known as being reduced or oxidized, respectively. An example of a half reaction for the formation of copper is a copper 2+ ion plus 2 electrons forms solid copper. The electrolysis of salt solutions can be used to restore artifacts and plate metal objects.